What if I told you that a simple heating blanket, the kind your grandmother might use on cold nights, helped dominate professional drag racing for 3 straight years? Not through any mechanical modification to an engine, not through exotic fuels or radical aerodynamics, but by warming up a bottle of gas to the temperature of a hot bath. Picture this. It's 1979 at US 41 Dragway in Morocco, Indiana. The air is thick with tire smoke and racing fuel. In the staging lanes, while other pro-street racers are checking spark plugs and adjusting carburetors, Pat Musi is quietly wrapping what looks like an electric blanket around his nitrous bottles. Other racers notice but don't think much of it. Maybe he's worried about the bottles getting too cold. Maybe it's superstition. What they don't realize is that Musi has discovered something that will revolutionize nitrous oxide systems forever, and he's about to use basic thermodynamics to embarrass every other racer on the property. This is the story of how an Indiana mechanic outsmarted the entire NHRA rulebook with nothing more than heating blankets, some thermostats, and a deep understanding of gas physics that his competitors had completely overlooked. To understand why Pat Musi's discovery was so revolutionary, we need to travel back to the late 1970s pro-street scene. This was grassroots drag racing at its finest, wild, barely controlled, and constantly pushing boundaries. Pro-street cars were street-legal machines transformed into quarter-mile monsters. We're talking about Camaros, Mustangs, and Novas, with massive tunnel ram intakes poking through their hoods, fat slicks barely contained by tubbed wheel wells, and enough horsepower to tear the asphalt off the starting line. Nitrous oxide was the great equalizer in pro-street. While the big-money teams could afford exotic engine combinations and constant rebuilds, a smart racer with a good nitrous setup could compete with anyone. The technology was relatively simple. Nitrous oxide, stored as a liquid under pressure in steel bottles, would be released into the engine where it would break down at combustion temperatures, releasing extra oxygen. More oxygen meant you could burn more fuel. More fuel meant more power. A basic 150-shot kit could add 150 horsepower instantly, stack multiple systems, and you could add 300, 400, even 500 horsepower at the push of a button. But here's where it gets interesting. Every nitrous racer in 1979 knew the basics of how the systems worked. What they didn't fully understand was how temperature affected everything. See, nitrous oxide exists as a liquid in the bottle only because it's under pressure. The pressure in that bottle is directly related to temperature. At 70 degrees Fahrenheit, a full nitrous bottle has about 760 psi of pressure. At 90 degrees, it jumps to 940 psi. The higher the pressure, the more nitrous flows through the jets when you hit the button. More flow equals more power. Most racers kept their bottles at ambient temperature, whatever the weather gave them. On a cold morning, their bottles might be at 60 degrees, giving them only 675 psi and reduced flow. On a hot afternoon, the same bottle might reach 85 degrees and 900 psi. This temperature variation meant their nitrous systems were adding different amounts of power for every run. They'd jet their engines for average conditions and hope for the best. Some racers would put their bottles in the sun before a run, trying to warm them up. Others would store them in coolers, trying to maintain consistent temperature. But nobody had really attacked the problem systematically. Enter Pat Musi. Musi wasn't just another weekend warrior bolting a nitrous kit onto his small block Chevy. He was an engineer at heart, the kind of guy who would spend hours with pressure charts and flow calculations while other racers were bench racing at the local speed shop. Musi understood that consistency wins championships. You can have all the power in the world, but if you can't repeat it run after run, you're going to lose to the guy who can. Musi started with a simple observation. The NHRA rulebook specified everything about nitrous systems, bottle mounting, safety blow-off valves, even the type of lines you could use. But nowhere did it mention bottle temperature. As far as the rules were concerned, A nitrous bottle was a nitrous bottle. The sanctioning body assumed everyone was running at ambient temperature because, well, that's what everyone did. So Musi started experimenting. He knew from industrial gas handling that nitrous pressure increases predictably with temperature. He pulled out his vapor pressure charts and started calculating. At 90 degrees, about as hot as most racers ever got their bottles, nitrous pressure sat at 940 psi. But what if he went higher? At 100 degrees, pressure jumped to 1020 psi. At 110 degrees, 100 psi. And at 120 degrees, the pressure hit 1280 psi. Now here's the critical part that Musi understood and his competitors didn't. Nitrous flow through a jet is proportional to the square root of the pressure differential. When you increase bottle pressure from 760 psi to 1180 psi, you're not just getting a linear increase in flow. The physics of compressible flow meant that his 120-degree bottles were flowing approximately 30% more nitrous than bottles at 70 degrees. 30% more nitrous meant 30% more oxygen, which meant he could add 30% more fuel, which translated to roughly 150 additional horsepower on top of the base nitrous shot. Think about that for a second. While his competitors were fighting for every last horsepower through expensive engine modifications, Musi had found 150 free horsepower just by heating his bottles. No internal engine changes, no exotic parts, just temperature control. But discovering the advantage was only half the battle. Musi needed a reliable way to heat his bottles to exactly 120 degrees and keep them there. Too cold and he'd give up power. Too hot, and he'd risk exceeding the safety margins of his nitrous system. Nitrous bottles have safety blow-off discs that rupture at around 1/800 psi, and while 120 degrees was well within safe limits, going much higher started entering dangerous territory. Musi's solution was elegantly simple. He went to the local hardware store and bought electric heating blankets, the same type used for keeping pipes from freezing. These blankets could wrap completely around a nitrous bottle and provide even, controlled heat. But he needed precise temperature control, so he added adjustable thermostats to each blanket. The thermostats would monitor bottle temperature and cycle the heating blankets on and off to maintain exactly 120 degrees Fahrenheit. The entire system was hidden in plain sight. To other racers, it looked like Musi was just trying to keep his bottles warm on cold mornings. The heating blankets were black and unobtrusive. The thermostats were small boxes that could have been anything, switches, timers, whatever. Unless you knew exactly what to look for, you'd never guess that those simple blankets were worth 150 horsepower. The beauty of Musi's system was its consistency. Weather didn't matter anymore. Whether it was a 50-degree morning or a 95-degree afternoon, his bottles were always at exactly 120 degrees when he pulled to the starting line. While his competitors' performance varied with temperature, Musi's remained rock solid. He could jet his engine for one specific nitrous flow rate and know that's exactly what he'd get every single time. The heating system also solved another problem that plagued nitrous racers: bottle cooling during runs. When nitrous flows out of a bottle, the expansion causes dramatic cooling. A bottle that starts at 90 degrees might drop to 60 degrees after a hard pass, reducing pressure and flow for the next run. Musi's preheated bottles started with more thermal mass at a higher temperature, maintaining better pressure throughout the run and recovering faster between rounds. Let's dive deeper into the technical brilliance of Musi's setup. The heating blankets he used were typically rated at around 150 watts per bottle. For a standard 10-pound nitrous bottle, it would take approximately 20-30 minutes to heat from 70 degrees to 120 degrees. The thermostats Musi installed were adjustable units with a temperature range from 50 to 140 degrees Fahrenheit, with accuracy within plus or minus 2 degrees. He set them at 120 degrees and wired them through relay circuits that could handle the current draw of multiple heating blankets. The placement of the temperature sensors was critical. Musi experimented with different locations and found that mounting the sensor directly to the bottle body, about 1/3 up from the bottom, gave the most accurate reading of liquid nitrous temperature. This was important because the liquid and vapor phases in the bottle could have different temperatures, and it was the liquid temperature that determined the actual pressure. Musi also discovered that insulating the bottles after heating was crucial. He used foam pipe insulation and custom sewn covers to maintain temperature between rounds. This meant his heating system didn't have to work as hard to maintain temperature, and the bottles stayed more stable during the cool-down periods between runs. The nitrous jets in Musi's system were specifically sized for 1,180 psi bottle pressure, while a standard .063 nitrous jet might flow 175 horsepower worth of nitrous at 950 psi, the same jet would flow 225 horsepower worth at Musi's elevated pressure. But Musi went a step further. He had custom jets machined to precise dimensions that would give him exactly the flow rates he wanted at his specific operating pressure. This attention to detail meant he could tune his fuel system perfectly for the increased nitrous flow. The fuel side of the equation was equally important. More nitrous meant more oxygen, which meant more fuel was needed to maintain the proper air-fuel ratio. Musi increased his fuel jet sizes proportionally and added a secondary fuel pump to ensure adequate supply. He monitored his spark plugs religiously after each run, reading the color and heat patterns to verify his mixture was correct. Too lean, and he'd melt pistons. Too rich, and he'd give up power. The heated nitrous system required completely different fuel curves than standard temperature setups. Now, you might wonder why Musi stopped at 120 degrees. Why not go to 130, 140, or even higher? The answer lay in the balance between power and reliability. At 120 degrees, nitrous pressure was high enough to provide substantial additional flow, but still well within the safety margins of standard nitrous components. The solenoids, lines, and fittings were all rated for much higher pressures, typically 1,800 psi or more. But as temperature increased beyond 120 degrees, other problems emerged. First, the nitrous would begin transitioning from liquid to vapor more readily in the lines. Vapor doesn't carry nearly the oxygen content of liquid nitrous, so power would actually decrease if too much vaporization occurred. Second, the rubber seals in solenoids and fittings would begin to degrade faster at higher temperatures. Third, and most importantly, the safety margin decreased. While bottles were rated for much higher pressures, running consistently at elevated temperatures increased the risk of a catastrophic failure. During the 1979 season, Musi's heated bottle system was devastating to his competition. At the starting line, his Camaro would leave harder and pull stronger than cars with supposedly more powerful engines. Competitors couldn't understand how Musi's relatively mild 406 cubic inch small block Chevy was outrunning their 500-plus cubic inch big blocks. They assumed he had some exotic camshaft or secret cylinder heads. Some accused him of running illegal fuel additives. Nobody suspected the innocent-looking heating blankets. The consistency advantage was even more pronounced in elimination rounds. Drag racing eliminations require multiple runs in quick succession. Between rounds, there might only be 30-45 minutes to cool down, refuel, and prepare for the next race. Competitors running ambient temperature nitrous would see their performance degrade as their bottles cooled from the previous run. Musi's heated bottles would be back at exactly 120 degrees by the time he reached the staging lanes for the next round. This consistency allowed him to dial in his car more accurately and cut better lights, knowing exactly how hard the car would launch. Musi was methodical about keeping his secret. He would install the heating blankets in his trailer, away from prying eyes. The control switches were labeled ambiguously. When asked about the blankets, he'd give vague answers about preventing condensation or maintaining consistent temperature. Technically true, but not revealing the full story. He even spread disinformation, suggesting to other racers that heating bottles was dangerous and could cause explosions, playing on the general fear of high-pressure systems. The psychological advantage was enormous. As Musi continued winning, his competitors became increasingly frustrated. They'd copy his visible setup, his tire pressure, his launch RPM, his shift points, but still couldn't match his performance. Some spent thousands of dollars on engine upgrades trying to find the horsepower Musi had discovered for the price of a few heating blankets. By the 1980 season, Musi had refined his system even further. He added individual pressure gauges to each bottle, allowing him to verify temperature by reading pressure without removing the blankets. He experimented with different heating patterns, discovering that gradually ramping temperature over 30 minutes produced more consistent results than rapid heating. He even developed a pre-race routine where bottles would be heated to 125 degrees, then allowed to stabilize at 120 degrees just before the run, ensuring the temperature was perfectly uniform throughout the liquid. The 1980 season saw Musi dominate pro street racing across the Midwest. Race after race, his heated nitrous system provided the edge needed to win. He was setting track records at strips that had stood for years. At Indianapolis Raceway Park, he ran a 8.42 at 161 mph, numbers that should have been impossible for his engine combination. Tech inspectors tore down his engine after that run, convinced he was cheating. They found nothing illegal. The engine was actually mild by Pro Street standards, 11.1 compression, a modest solid roller cam, and conventional cylinder heads. The secret was in those 120-degree bottles. Word began to leak out during the 1981 season. A former crew member, bitter after a falling out with Musi, started talking to other teams. He didn't know all the details, but he knew the heating blankets were more than just warmers. Smart competitors began experimenting with their own heating systems. Some tried propane torches, which heated unevenly and were dangerous. Others used hot water baths, which were messy and impractical at the track. A few figured out the electric blanket solution, but without knowing the optimal temperature, they either ran too cold and gave up power, or too hot and experienced problems. The arms race escalated quickly. By mid-1981, several top pro street teams were running heated bottles, though most hadn't optimized their systems like Musi had. The NHRA began receiving complaints from racers who couldn't afford elaborate heating systems. There were also safety concerns. Some racers, not understanding the pressure limits, were heating bottles to dangerous temperatures. At a race in Ohio, a competitor's overheated bottle activated its blow-off disc in the staging lanes, venting the entire contents in a massive cloud that shut down racing for an hour. Musi, meanwhile, continued to innovate. He developed a second-generation system that used pulse-width modulation to control the heating blankets more precisely. Instead of simple on-off thermostats, his new controllers could vary the power to the blankets, maintaining temperature within 1 degree. He also began experimenting with bottle pressure during the run, using data acquisition to monitor how pressure dropped during a pass and adjusting his heating strategy to compensate. The data Musi collected was fascinating. A typical 10-pound bottle at 120 degrees starting temperature would drop to approximately 85 degrees by the end of a quarter-mile pass, running a 500 horsepower shot. The pressure would fall from 1,180 psi to about 890 psi. By studying these pressure curves, Musi could calculate exactly how much his nitrous flow was decreasing during the run and adjust his fuel curves accordingly. This level of analysis was unprecedented in pro street racing. Musi also discovered that bottle orientation affected temperature distribution. Bottles mounted vertically maintained more consistent temperature than those mounted horizontally. The convection currents in the liquid nitrous helped distribute heat more evenly in vertical bottles. He redesigned his mounting system to accommodate perfect vertical positioning, even though it meant relocating other components in his Camaro's trunk. The end came suddenly. At the 1982 NHRA Spring Nationals, the sanctioning body announced an emergency rule change. Effective immediately, nitrous bottles could not exceed 90 degrees Fahrenheit at any time during competition. Tech inspectors would be equipped with infrared temperature guns to check bottles in the staging lanes. Any racer found with bottles over 90 degrees would be immediately disqualified. The rule change sent shockwaves through pro street racing. Teams that had invested thousands in heating systems were suddenly back to square one. Musi's 3-year advantage evaporated overnight. But here's the thing about innovation. Once knowledge is released into the world, it can't be taken back. The entire nitrous industry had learned from Musi's discovery. Within months, nitrous manufacturers were selling temperature-controlled bottle warmers that would maintain exactly 90 degrees. They developed new solenoid designs that could handle higher flow rates at legal pressures. They created better jets optimized for consistent temperature operation. Looking back, Musi's heated bottle innovation represents everything that makes Grassroots racing special. It wasn't developed in a corporate R&D lab with million-dollar budgets. It came from one smart racer with an understanding of physics and the creativity to see opportunity where others saw limitations. The total cost of his original heating system was less than $200, the price of heating blankets, thermostats, and some wiring. Yet it delivered performance that competitors couldn't match with $20,000 engines. The technical legacy of Musi's discovery extends far beyond drag racing. Today, every professional racing series that allows nitrous oxide has specific rules about bottle temperature. NASCAR, NHRA, IHRA, they all learned from what happened in Pro Street. Modern nitrous systems come with integrated heaters and precise temperature controls, technology that traces directly back to Musi's heating blankets. The current standard in professional drag racing is to maintain bottles at exactly the maximum legal temperature using systems that would seem like science fiction to 1979 racers, but operate on the same principles Musi discovered. The physics hasn't changed. Temperature still determines pressure, pressure still determines flow, and flow still determines power. What's changed is that everyone now understands these relationships. Nitrous system manufacturers publish detailed charts showing flow rates at different temperatures. Electronic controllers can adjust fuel delivery based on bottle temperature sensors. Some systems even compensate for temperature drop during the run, adding fuel as nitrous flow decreases. Modern Pro Mod and radial racing cars, the descendants of those original Pro Street machines, use nitrous systems that would seem like magic to 1979 racers. Multiple stages of nitrous, each with its own temperature-controlled bottle. Progressive controllers that ramp power in gradually to manage traction. Data logging systems that record bottle pressure every hundredth of a second. Total nitrous shots exceeding 1,000 horsepower. But at their core, they're all using the principle Pat Musi proved with heating blankets and determination. That controlling nitrous temperature is just as important as the nitrous itself. The story also highlights how racing rules evolve in response to innovation. The NHRA didn't ban heated bottles because they were unsafe. 120 degrees was well within safety limits. They banned them because one racer had found such a significant advantage that it threatened competitive balance. This pattern repeats throughout motorsports history. Someone finds a loophole, dominates until others catch up or rules change, and the cycle continues. It's what drives innovation forward. Musi himself went on to become one of the most successful engine builders in drag racing. Pat Musi Racing Engines has powered countless championships in NHRA Pro Stock and other categories. His daughter Lizzie Musi became a professional drag racer herself, carrying on the family tradition. But those who knew Pat in the early days remember the heated bottle episode as his finest moment, outsmarting an entire sport with basic thermodynamics and hardware store parts. What really makes this story remarkable is its accessibility. Musi didn't need a degree in mechanical engineering to figure this out. He didn't need sophisticated test equipment or computer simulations. He needed curiosity, systematic thinking, and the courage to try something different. He looked at the same nitrous bottles everyone else was using and asked a simple question: what if they were hotter? That question led to 3 years of domination and changed nitrous racing forever. Today's racers might laugh at the simplicity of heating blankets and mechanical thermostats. They're used to laptop tuning and electronic everything. But the principle remains profound. Sometimes the biggest advantages come from the simplest ideas. Sometimes the solution is hiding in plain sight, waiting for someone to connect the dots. Sometimes a grandmother's heating blanket is worth more than a fortune in exotic parts. The heated bottle saga also demonstrates the importance of understanding the complete system, not just individual components. Musi's competitors focused on engines, camshafts, cylinder heads, compression ratios. They understood those components deeply. But Musi understood that the nitrous bottle was just as much a part of the engine system as the pistons and rods. By optimizing a component others ignored, he found performance that couldn't be matched by traditional modifications. Consider the elegance of the solution: no moving parts to break, no exotic materials or complex machining, no risk to engine reliability, just simple resistance heating and basic temperature control. The same principles that keep your coffee warm could add 150 horsepower to a race car. It's a reminder that engineering brilliance doesn't always mean complexity. Sometimes it means seeing simplicity where others assume complexity is required. The economic impact was substantial, too. Before Musi's innovation became public, racers were spending fortunes chasing horsepower through traditional means. A set of racing cylinder heads might cost $5,000 and add 50 horsepower. A custom camshaft could be $1,000 for 30 horsepower. But Musi's heating system delivered 150 horsepower for $200. Once the secret was out, it democratized performance in a way that expensive engine modifications never could. The story continues to inspire today's racers and engineers. In forums and tech discussions, you'll still see references to pulling a Musi, finding a clever loophole that delivers unexpected performance. It's become part of racing mythology, a reminder that innovation doesn't always come from the biggest teams or deepest pockets. Sometimes it comes from one person willing to question conventional wisdom. Even now, over 4 decades later, racers still debate what might have happened if the NHRA hadn't changed the rules. How hot could bottles safely go? What other advantages might temperature control provide? Some argue that Musi's 120 degrees was conservative, that 140 or even 150 degrees would have been safe with proper precautions. Others point out that the rule change probably prevented serious accidents as less knowledgeable racers tried to copy Musi's success without understanding the limits. The technical documentation from that era is fascinating. Musi kept detailed logs of every run: bottle temperature before and after, ambient temperature, humidity, barometric pressure, nitrous pressure, jet sizes, spark plug readings, and of course, elapsed times and speeds. These notebooks, now part of drag racing history, show the methodical approach that separated him from weekend warriors. Each page reveals adjustments and observations, building toward the optimized system that dominated for 3 seasons. What Pat Musi did with those heating blankets was more than just win races. He proved that in racing, like in life, the biggest advantages often come from seeing what everyone else misses. He showed that understanding the science behind the sport is just as important as seat-of-the-pants feel. He demonstrated that innovation doesn't require permission or massive budgets, just observation, experimentation, and the courage to be different. The next time you see a drag race, whether it's professional NHRA or local bracket racing, look for the nitrous bottles. They'll likely have heating systems, maintaining legal temperature for consistent performance. The racers using them might not know the full story, might not realize they're using technology pioneered by an Indiana mechanic with hardware store heating blankets, but the legacy lives on in every temperature-controlled nitrous pass, a reminder that sometimes the best solutions are hiding in plain sight, waiting for someone clever enough to spot them. That's the beauty of grassroots innovation. It doesn't ask permission. It doesn't wait for approval. It just sees an opportunity and takes it. Pat Musi saw that opportunity in 1979, and drag racing has never been the same since. What's the most clever racing innovation you've ever seen? Drop a comment below and share your favorite story of backyard engineering beating big money teams. And if you enjoyed this deep dive into drag racing history, make sure to subscribe for more stories of the brilliant minds who pushed motorsports forward with nothing but ingenuity and determination.